Welcome back for this second lecture in the series of lectures where I explain the kinetic theory. Of course, I have first of all to establish the theory for the gases, and so from what we learned from chemistry and physics too, we'll talk about the behavior of gases. And we study them at low pressure and high temperature. If so, then experimentally we obtain a relation that is the product of the pressure and the volume is equal to a constant times the absolute temperature in Kelvin, where this constant can be written as N into K. In fact, this K is equal to Kb, the Boltzmann constant, which is same for all gases and which is equal to 1.38 into 10 to the power of minus 23 joules per coulomb. So, with the studies of these gases, we find out that if a gas has the parameters P1, V1, N1, T1 and P2, V2, N2, T2 in two situations, then P1, V1 is equal to P2, V2 is equal to N1, T1 is equal to N2, T2 is equal to the constant, and this constant is defined as the Boltzmann constant. Okay? So here, look, for the same set of PVT, N is also the same, which recalls Avogadro, who could say that a molar mass of any gas at STP, standard temperature and pressure, of temperature of 0 degrees Celsius and pressure equals to 1 atmosphere. For 1 mole, N is equal to Na, which is Avogadro's number, is equal to 6.02 into 10 to the power of 22. 23, I'll just check, it's 22. This is 20. Okay. Anyway, you can always make corrections and learn the proper thing. Now, let us see as to what is a perfect gas equation. A perfect gas equation pertaining to what is known as the ideal gas is PV is equal to nRT, where R is the UGC, universal gas constant, okay, not the universal gravitational constant. The gas constant is 8.314 joules per mole per Kelvin. Okay. Now we can write the number of moles N is equal to the mass of the gas containing N molecules, which is capital M, and the molar mass, which is MO. Okay, these masses are in the same units. So this got to be a number, and this is given by N divided by Na, and this is the number of moles. So what we have is, we can write PV is equal to Kb into Nt from this relation, this set of relations. PV for any value of P and V, an associated value of T, and the number N, this is equal to, okay. So I can write now the value of P, I divide this equation by capital V and I get it as Kb nu T, where nu is the number density of molecules. The number density of molecules, to how many number of molecules are there in a single meter cube. We also get another useful form of the same equation. I can write P is equal to rho RT divided by M naught. Okay, where rho is the mass density of the gas. You can derive this equation from these equations from simple definition of rho, etc. Okay. Now, the behavior of these gases is close to that of an ideal gas, which I showed by the perfect gas equation over here. This ideal gas is a simple theoretical model. It's a simple theoretical model. It's a theoretical model. It's not anything which the reality is able to touch. Now what we do is, in this equation, if I fix N, the number of moles, and the absolute temperature, capital T, then PV is equal to a constant, which is nothing but, because the temperature is constant, then that is a curve which we call an isotherm, okay, which pertains to this is P and this is V. So we get, on a linear scale, we will get a curve like this, where every set of P1, V1, P2, V2, etc. will have the same area under the curve. Okay, so this is what is described as the old friend, what is known as the Boyle's law. And similarly we can get an if instead of that we keep the pressure constant, then there is a relation between the V and T, and that is about Charles' law, where we'll get the isobars. Okay. Okay, here we make 23. So looking at the behavior of gases, I told you that there is a friendly Boyle's law and Charles' law that we have learned in our high school classes, in chemistry classes, also in physics classes. In Boyle's law, there is no change in the temperature. Delta T is equal to 0. So we have PV is equal to constant, and we get isotherms, which pressure versus volume, as I've shown, they go something like this. On this side will pop up 3 diagrams which are drawn to scale, and they need your attention in understanding the behavior of the gases at low pressures and high temperatures, etc. They are all given there. You got to read the graphs, and you got to develop your ability to read the graphs and how the graphs are changing, and what is the experimental result and what is the theoretically calculated results. They are all exhibited over there. They need your attention, and that is how you have to learn about the Boyle's law. In the Charles' law, where the pressure was kept constant, there is no change in the pressure, and the voltage is proportional to, the volume is proportional to temperature, and we get instead isobars like this, and we'll get some theoretically calculated curves like this for various pressures P1, P2, P3. I don't have the ability to draw these graphs to the scale, and therefore I'm asking you to look at the real display of the isobars and isotherms and the behavior with the ideal gas that is there. So these are the two things we had to mention before we indulge ourselves into developing a kinetic theory of gases, explaining pressure, temperature, and many other aspects while doing so. Of course, remember that the molecules of a gas, they are far apart, and in developing the kinetic theory of gases, we understand that the interaction among the molecules, which we call collisions, that we ignore as compared to the perpetual motion of the gases and their interaction among themselves and also with the walls of the container. So the next item that I would like to address is, we would like to have what is known as the Dalton's law of partial pressures, okay, in which we take a mixture of non-interacting gases, gases which do not chemically interact with each other to give another gas, okay. They have their independence, okay, and anyway, they do live together, they stay together, and let us say that for a vessel of volume V having a temperature capital T and a pressure P, let there be N1, N2, N3 moles, etc. of the non-interacting gases. In doing so, we write the equation PV is equal to N1 plus N2 plus N3 per N pro, etc. Into RT. Okay, where N1, N2, etc. are the number of moles of those non-interacting individual gases. So I can write it as N1 RT plus N2 RT plus N3 RT, etc. like that. We don't confine as to how many gases are there in the mixture. As many gases as you like, but we must know in conducting the experiment as to what is the number of moles associated with each gas. Now, I can write from this equation, I divide it by V, etc. And this becomes equal to, by definition, this becomes equal to P1, P2, P3, etc. So that the pressure of the mixture is equal to the pressures of the individual gases. When they occupy the same volume at the same temperature, okay, and we can measure those when there is no other gas in that environment, in that way. So we have the equation P is equal to partial pressure P1 plus partial pressure P2 plus partial pressure P3, etc., etc. And this is known as the Dalton's law of partial pressures. Friends, I'm not going to undertake that, but there is an advice, and the advice is, I give you an advice that you must attempt, not only attempt, but to solve the many problems associated with Boyle's law, Charles' law, etc., etc. And there you will enjoy, and you will see, for example, in the case of water, vapor, you will find that the intermolecular distance in that case is, for a given STP, etc., you can calculate it to be in the nearness of 2 Armstrong degree. Okay, and many other things you can calculate, and you will be fascinated by attempting such questions which pop up anywhere in any text. So that is a must for you. And before I go and we go for the kinetic theory of gases, their postulates and how that they function. So let us develop the base of the kinetic theory of an ideal gas. And in the beginning I will tell you that whatever things we are going to relate here with the molecular kinetic theory of gases, in particular the ideal gas that we are going to take, ideal gas which exists at low pressures and high temperatures. Now, there are several things which we have to understand and how things happen before we go to explain to you as to what is pressure, what is temperature, etc. according to the kinetic theory of gases. The same kind of postulates are also taken in the free electron theory of metals, okay, or free electron gas. There also we have similar kind of, not exactly this, but similar kind of things, and the results of the kinetic theory of gases are taken and we explain the other things. So that will be easy when we come to that, if you master this, if you understand this. Now, according to the kinetic theory of ideal gases, gases are a collection of large number of molecules, and this number is approximately of the order of Avogadro's number, 6.02 into 10 to the power of 23. Okay. Because normally when we consider gases at STP or other temperatures and pressures, then they are of the order of about 22 liters of gas which can be contained, which we can understand in a laboratory context. Now, the average distance between the molecules is several tens of the molecular size, which is approximately equal to 2 Armstrong. 1 Armstrong is equal to 10 to the power of minus 10 meters. Well, the molecules are in incessant random motion, which follow Newton's first law, and there are straight paths that the molecules are supposed to cover in a straight line. Okay. So Newton's first law, a body continues in its state of rest or of uniform motion unless impressed by an external force. Okay. When the molecules, they come close, they experience intermolecular forces which are repelling in nature. Earlier, in the days when I was a student like you, I was told that there are collisions between molecules. But actually collision means they come in physical contact with each other, but the intermolecular forces, they don't allow them to come very close to each other, like in the case of a collision of a ball that you can see with another ball or with the floor or ceiling or the walls. So they experience intermolecular forces. As a result, velocities change. They also collide incessantly, without stopping, time and again, against each other or with the walls of the container. Velocities change. Velocities change. Velocities change. When I say so, it means that the magnitude of speed and the direction may change according to what kind of interaction they have with each other and with the walls of the container. The interesting thing is that we consider these collisions to be perfectly elastic collisions. Okay? So therefore, the total kinetic energy of the system is conserved, and also the total momentum is conserved. So with that, we consider a cube of side L. It's not necessary to take a cube, but it's of convenience to us to choose a cube of side L. Of course, a cube has 6 faces, three pair of faces parallel to each other, and the face area is equal to L square. We take the mass of the molecule to be equal to m, and there is a time, a small amount of time in which we consider the interaction of these molecules with the walls of the container. In this small interval of time, maybe some of them may be heading towards the wall, and while others may come away from the wall. Okay, so naturally, if we take one of the faces, then we find that, like the law of reflection, the angle of incidence is equal to angle of reflection, kind of a thing is there. So I've just shown to you as that the change is taking place only along the x-axis, and we have the velocity of the molecule Vx, Vy, Vz, which changes to minus Vx, Vy, Vz for this face over here. Okay. Which we can see that Vx, Vy, Vz, Vx, Vy, Vz, they are mutually perpendicular and they are independent of each other. So taking that cue, we can say that the change in the momentum which is imparted to this particle which is coming and having a collision, here we can talk about real collision, taking the rigid wall over here, and then the velocity, incident velocity is Vx and the reflected velocity is minus Vx, and therefore the change in the momentum of the particle with the mass m, this will be equal to minus mvx minus mvx. That is this momentum minus this momentum. Turns out to be equal to minus, for a single molecule we are talking about in direction x. Okay, so therefore this is the change in the momentum, and the momentum imparted to the wall is equal to 2mvx. So what will happen? The momentum is there and there is a time in which this is taking place, so we can talk about the rate of change of momentum, so that there is a force, and when the force is there, we calculate the force and then divide it by the area of cross section of the system, and consider that whatever we are doing in the x direction is true for the y direction and also true for the z direction. So we have, for the set of velocities Vx, Vy, Vz, all the 6 phases, they allow us to have the same kind of physics, and we obtain the same pressure on all the walls of the container. This is what I am going to follow, okay, in the next few moments. So with our build-up, a molecule with an x component of velocity Vx will hit the wall, that is the YZ plane, if it is within a distance of Vx into delta t from the wall. Delta t is the time that we have taken as it is. Therefore, all molecules within a volume A multiplied by the Vx into delta t only can hit the wall in time delta t. Okay, they can hit. But provided all of them are moving in the same direction, which cannot be true. On the average, half of them, half of the total molecules move towards the wall, and the other half, they will move away from the wall. It's very simple, logical. So the number of molecules hitting in time delta t, having the velocities vx, vy, vz, okay, towards that particular plane, that is the yz plane, that will become equal to half of the total value, where half into a delta vx delta t, okay, a vx delta t multiplied by n, where n is the number of molecules in a single, per unit volume, okay. So a total momentum transferred to the wall in time delta t, that I am writing as q, not even as small p, because capital P we are taking for fluid. Just to distinguish, we are taking q. It is how much? 2 mvx per molecule into the total number half n a vx delta t. And so the force on the wall will become equal to the momentum divided by the time, rate of change of momentum, okay. That's Newton's second law. So the pressure becomes equal to, by definition, force divided by area, and force is equal to q upon delta t divided by area, and this becomes equal to q upon a delta t. So from here it becomes equal to nmvx square, okay, for a single molecule, okay. Vx is the velocity. Now on the average, I should rather write that on the average the pressure will be equal to nm into vx square average value when we take the mean value. And by the way, I must tell you and share with you what is the difference between average and mean. The average can be taken of so many people, the age of the country, where the people are 100 years old and the people are not even 100 seconds old, taking their living life together, dividing by their number, you will get the average. What is mean? In taking the mean, the value should be approximately equal. So in your class or in your section, there are so many colleagues, and they age between say 16 to 18, like that. There, because the data are very close together, we take the mean, and this mean which we are taking over here is arithmetic mean. So the arithmetic mean here, the average value, the mean value, okay, Vx square, and we are putting a bar over there for that. Now, like Vx, we have Vy, like Vy, we have Vz, and they are, rightly we can take their average values, their mean values of the squared velocities to be equal to each other. The simple logic says that this will be 1/3 of this square plus this square plus this square, which we get over here, and this square plus this square plus this square is equal to v square average, okay, where v is the speed and v square is the mean of the squared velocity, okay. And so if you subscribe to that, then P becomes equal to 1/3 mnv square, which we can write as 1/3 mv mean, squared mean, where n becomes equal to nm, etc. So you can see that if we know n, if we know m, and like we have the explanation of v square average or mean of that value, then the pressure can be expressed in terms of these things here, and it is interpreted. So this is how the interpretation of pressure is there in the kinetic theory of gases. Look here, in this final equation, there is no mention of the area of the wall or the time that we have just imagined that this is the time in which this thing is happening. Both these terms do not appear in the final result, and therefore we can say that, of course, we have taken a cube, but I could have taken any shape, and the pressure is not a function of the shape, etc. of the container. Friends, this is where I leave you today, okay, to be versed with this, and in the next outing I will explain out to you what is the interpretation of temperature, etc. in the kinetic theory of gases, and proceed from there to explain many other things. Thank you very much for being with me. Please do it before you come for the next lecture. Okay? Thank you very much.